Okay, welcome to this video. We are going to look through all of our study guide problems and solve them, and we'll see how quick these problems can be. We have a 35 kilogram balloon, which is being pushed by 4 different forces. These are all different forces shown below. So the first thing you see, okay, there's the force of gravity, there's the 95 newtons, 260. Those two forces, 260 and 95, are different. So 260 has its own x component and its own y component. 95 then, 95, this one, is totally separate and totally different from the x part of 260. Okay. So the question, you might be thinking, is 95 the x component of 260? Decidedly, the answer is no. Okay, we're viewing the balloon from the side, so we're not looking at east, west, north, south. We're looking at left, right, up, down. Okay, and we have to find the magnitude and direction of the resultant force on the balloon. The way that we find the resultant force when we have lots of forces being added is by finding the total x force, the total y force, and using the Pythagorean theorem, which I just wrote down. A squared plus b squared is c squared, right? That's what we're going to use. But first, before we do it, we need to know the total x force and the total y force. We can only find the total x and total y forces if we know what all of the x and y components are for the 2D forces. Those two forces that I just underlined have an x part and a y part, and we have to know those two parts, the x and y parts, to add up the x's and to add up the y's. So our first task, we just figured it out. Our first task is to draw the x and y components like that. Okay. Then we're going to add up the total x force. We have 3 forces pointing along the x-axis, right? There's the 95 pointing right. Because it's right, it's positive. There's the x part of 260. It's also right, so positive. And its value is 260 cosine 71 degrees. And then there's the x part of 205. It points left, so it's negative. And the value is 205 cosine 71. We plug this into our calculator, and what do we get? What we get for the total x force, I'm going to erase this because I've got limited room. We get negative 7.63 newtons. And the negative sign tells us it points, the total x force is to the left. Like that. Now let's do the same thing, find the total y force. Same thing, but with the y-axis forces. Remember, we got rid of these. We can squiggle those out because we already took care of them by breaking them into the components. So they're no longer part of our picture. Okay, so we've dealt with all of the x's, now we deal with all of the y's. It's a very wise thing to do. Oh, yuck, 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 yuck. Okay, first I will add up the y part of the 260 Newton force. It points up, so it's positive, and the value is 260 sine 71. Then I have the y part here of the 205 Newton force. That y part points up, so it's positive as well. And the value is hypotenuse sine theta. And then finally, I have my final force in the y direction is Fg. It points down, so it's negative. And Fg is just m times g, so 35 times 9.8. And what's 35 times 9.8? 343. So the value is 343. It points down, so negative 343. I don't put negative. I personally don't put a negative in my picture Negative 343, because the arrow is showing the negative. I only use the negative when I'm adding up the total X force here. Okay, now that I've got all those written down, I can find the total Y force, and what do you get? This all comes out to negative, and I'm erasing because I have limited space, but you definitely want to show this work. You have negative 13.8 newtons. All right, then I can come back to this equation, right? And I can erase total X force, and I can replace it with the negative 7.63, or just 7.63. I can erase total Y force and replace it with the 13.8. And what do I get for the total force? Whoa! Crazy. Hang on. Let's just move those down. What do I get for the sum of the forces, the resultant force, the net force? It has so many names. 7.60 squared plus 13.8 squared. And this is about 16 newtons, like that. Okay. Now I'm going to put here's my hot air balloon, just my balloon. And I'm going to draw the net force. The total X force is to the left, the total Y force is down, so the total force is like that. Now I need to find theta. Right? Theta, I can see clearly, is going to be inverse tangent of the total Y force over total X force. And it's going to be pointing down from horizontal left. That's the direction theta will have. So I'm going to take away this so I have room. And I find theta, inverse tan of opposite over adjacent. So the, let's see, it was 13.8 over 7.63. You plug that into the calculator, make sure you're in degrees mode, and you get 61 degrees. By looking at the picture, I see that it's down from horizontal left. So I've skipped a lot of work because I didn't have much space. You want to make sure I showed the work, but I erased it. Don't erase your work, show all of your work. Okay, find the magnitude and direction of the acceleration. We know the acceleration is equal to the total force, the net force, divided by the mass. So you take your 15, let's see, the unrounded total force, which was 15.77, divide by the mass, and what do we get when we take that unrounded total force? We get 0.45 meters per second squared. And of course, theta for the acceleration is the same as what we found before. So if the total force points along this angle, then the acceleration, which is just smaller because it's 0.45, the acceleration points in the same exact direction. They always have the same direction. If you push at an angle, then you accelerate the thing at the same angle. So it's 61 degrees down from horizontal left. Next problem. Below is shown a system of 3 ropes and a 15 kilogram mass. The system is in equilibrium, so probably not moving. There's no way it could have constant velocity, so when they say equilibrium, we know they mean it's at rest. The tension in the left rope, let's draw it. T, the ends have been stretched, is equal to the tension in the right rope, so this is the same T. We don't need to distinguish T1 from T2, they're the same. Find the tension in each rope. Alright, we have, for each of these tensions, an X part and a Y part, Ty. The hypotenuse is T, So let me move the T over to the hypotenuse. Now, on the block, gravity pulls down with mg. M is 15, g is 10. So we get 150 newtons as the force of gravity. The weight is 150 newtons. That means the tension in this rope is 150, and the tension pulling down right there is also the same, 150. 150 newtons. The trick with these problems is to balance the y forces. So first, let's say equilibrium, forces, balance, because of that word right there. So the up forces balance the down forces. The two forces pointing up are Ty and Ty. Together they make 2 Ty. They are equal to each other because the hypotenuse is equal, and theta is the same, 25. That's what pulls up, 2 Ty. What pulls down is the 150 newtons of tension in that bottom rope. This bottom rope here. And so we solve for Ty, and we get 75 newtons. And then we replace Ty with T sine theta, which in this case is 25. Right? Ty is replaceable with T sine theta, hypotenuse sine angle. And when we solve for T, 75 divided by sine of 25 is 177 newtons. All right, next problem. A horizontal rope is attached to a wall as shown below. A person's pulling the rope to the right so that the rope is taut and is not moving. Aha! Forces balance. Balancing. Balancing? F's balancing? Trying to write this late at night is a balancing act. F's balances. Oh my gosh, this is just embarrassing. Okay. So what's the tension? The magnitude of the tension, ignore the negative or positive, left or right, in the left end of the rope. Here's the left end, here's the right end. The person pulls with 25 newtons. The string, as a result, has been stretched out. The ends have been stretched. And the rope, the string, resists the stretching, so the ends are pulled back in with the tension. The force pulling the ends toward the middle, we call the tension. And this end, likewise, is pulled with the same tension. So if this point is in equilibrium, that point is in equilibrium, so the tension must be 250. I'm sorry, the tension is just 25. The tension must be 25. And the tension is equal in the two ends because tension is distributed evenly through an ideal rope. So we have 25 newtons as the tension at the left end of the rope.